Welcome to today's webinar on keys to analyzing response surface designs. This is a follow-up webinar to one I gave about a month ago, which was keys to building a response surface design. In that one, we talked about central composite designs, box Benken designs, and optimal designs. And so we are going to just continue that conversation, but now get into the analysis of any response surface design. We will be keeping the attendees muted today. If you have questions, you can ask them, post them in the question area. I will try to address them during the webinar, but if I don't get to your question, I will reply via email afterwards. You can also send questions to stathelp@staties.com. and one of our experts will get back to you. Give me 1 second here. I am looking for my, there. Okay. Response analysis, response surface analysis follows a nice pattern. And so these are the steps that we're going to go through today. We are going to look at something that we call the fit summary screen. We're going to look at the ANOVA and some of the fit summary statistics. We're going to look at diagnostics, a little bit about model reduction, and then finally we will talk briefly about confirmation runs. The case study that we're going to use is in our tutorials. So if you go into Design Expert or Staties 360 and you go to Help and then Tutorials, you can find the tutorial for response surface chemical conversion, and that is the case that I'm following today. If you go to Tutorials Data, look for the chemical conversion file. So this particular case has two responses, percent conversion and activity. We are only going to look at conversion in this webinar. There are three process factors: time, temperature, and catalyst, and they have been put together in a central composite design. This design was run in 2 blocks. They couldn't get all the runs done in 2 days or in 1 day, so they split, they asked the software to split the runs into 2 blocks. As a reminder, a central composite design is formed by taking a 2-level factorial design. That is the blue dots here. These help estimate our linear effects and our 2-factor interactions. Then to this, we add center points. Center points are replicated to help us estimate the pure error of the design. And they also help, in this case, tie the blocks together, since we have a few center points in the first block and a few more in the second block. Then the center points, along with these axial or star points, provide enough information so that we can estimate the pure quadratic effects. In Design Expert or Staties 360, the analysis is laid out quite nicely from left to right, starting with a configure button. The configure button is where you can optionally add a transformation to the data. We normally start without a transformation, so there's a button on this page that says Start Analysis. We'll start with that. And then we go to a report called the Fit Summary Report that provides comparative statistics on polynomial models. So we'll look at that in this session. Then we go on to the model screen, where we can actually select the model that we want to form the ANOVA for. In the ANOVA, we get to check the model and the lack of fit, p-values, r-squareds, etc. Then we use diagnostics to validate the model, and finally wrap up with the model graphs where you're viewing pictures of the polynomial that you created in the ANOVA. Let me gonna show this in Design Expert. Whoops, wrong screen. Okay, so here's the design in Design Expert. I will even turn on the space point type so you can see that the first day we did factorial points and center points. And then in the second day, we did axial points and additional center points. Okay, so to start the analysis, we are going to click on conversion, and we are going to click on the button here that says Start Analysis. But just a side note, this is where you can choose a data transformation if, after analyzing it the first time, the diagnostics indicate that it would be better analyzed with a transformation. So we are going to start the fit summary, which is a feature that's unique to Design Expert. Most of our competitors would require you to fit a linear model and check it out, and then go back and fit a two-factor interaction model and check it out, etc. So you have to go through a series of models. In Design Expert, we decided to give you a quick view of each of these models. So I'm going to blow this up, go back to my notes. Here we go. The first column is looking at the p-value for each of the sets of terms. So we start by considering the linear terms. And this design was a three-factor design, so the linear terms would be A, B, and C. And we calculate the total p-value for A, B, and C, and we can see that it is not significant. It's greater than even 0.1. We would want the p-value in general to be less than 0.05. And the linear terms are showing that they are not significant. Okay, so then what we do is we add the two-factor interaction terms. So that would be AB, AC, and BC. We add that group of terms, and we test that group of terms against the linear terms. That's why this is actually called a sequential p-value, because we are going to test each set of terms against the preceding set. And so the addition of the two-factor interaction terms adds significance. Those are significant, so that is good. We go down and add the next set of terms, the quadratic terms, to the 2FI model. And again, those additional terms are also significant, so that is also good. We then add the cubic terms, which are actually aliased. That means that we cannot add all of the cubic terms. We can just kind of look at the cubic terms as a set and just ask, is there any cubic behavior in this? And the answer is no, those terms are not significant. A central composite design would not allow you to choose a cubic model, not even individual cubic terms, because they are aliased with each other. They are confounded or confused with each other. So we can't do that, but we can test them as a little group just to see if there's any possibility that they're needed. So the first guideline is to go to the highest order polynomial where you have some significant terms. And so that would be the quadratic. The next column of information is something called the lack of fit. Now, we want our model to fit. We want the model to fit the data. And so significant lack of fit is bad. That means the model does not fit. So this p-value, the linear model of 0.04, indicates that linear model has significant lack of fit. It does not fit the data. Okay. Once you add in the two-factor interactions, then you are starting to fit the data. That's good. And the quadratic model is very good, very non-significant lack of fit. Now, honestly, as long as the lack of fit p-value is above 0.1, it's good. It does not have to be a super high. It's nice if it is, but it doesn't have to be. I'm going to go forward a slide and illustrate this lack of fit, and then we'll come back to the R-squared values. So let's just say that I have a single factor that I'm looking at, I'm measuring. I'm measuring it in 6 locations. So this is my x-axis. So I take my factor and I measure it once, and I measure it, measure it at level 1, and I measure it 2 times. And I go to level 2, and I measure it another 2 times, and at level 3, another 2 times, etc. So I have six levels, and I'm measuring 2 times at each level. So I have replicates. And then I fit a linear model through this. So we do a least squares regression, and we fit a linear model. Now, you can see visually how much this linear model is not fitting the data. There is significant lack of fit here. You don't even have to do a test. You can just visualize this, look at this, and see that the data is definitely not fitting that model. If we fit a quadratic model to this, we're going to end up getting insignificant lack of fit. You can see now how nicely that model fits the data. Now, the test that's performed compares the variation between the actual data and the predicted value. Okay, so thinking about that, this is the numerator. It's comparing the difference between the actual data points, so you have 2 data points here, and the prediction. The prediction is where the line is. That's the prediction. So you compare that variation, and here we have these 2 points. Their prediction is here, so we compare that variation and this variation. Okay, all of that variation is compared to the variation between the replicates. And so we look at each of these sets of replicates, and this is all calculated using sums of squares. So you take these differences, square them, and sum them up, and that will become the denominator. These 2 types of variation should be similar in size. That would give you an F-test that's close to 1, and it would be non-significant. Now, one key in the lack of fit test that sometimes gets overlooked is that if your design does not have any replicates, if you chose to not do any replicates, then you cannot get a lack of fit test. The lack of fit test requires replicates. So do your replicates in order to take advantage of that lack of fit test. Okay, so I'm going to go back to our fit summary screen. The last 2 columns in fit summary are the adjusted and predicted R-squared values. And the adjusted R-squared value tells you the amount of variation in this data that is being explained by this model. So the linear model is explaining about 13% of the variation in the data. The 2FI model is explaining about 58%. The quadratic model is explaining about 88%. Okay, so higher is certainly better, closer to 1 is better, but when you're comparing models, just a higher number is better. The predicted R-squared tells you the amount of variation in predictions of the future that's explained by this model. Okay, a negative predicted R-squared is very bad. That means that the overall average of the data is just as good of a predictor as the model. So not a good result. But here, the two-factor interaction model is explaining 36% of the variation in predictions, and the quadratic is explaining 78% of the variation predictions. So all good. The desired model, the best model, should have a difference between adjusted and predicted of no more than about 0.2. So we want higher R-squareds with a difference less than 0.2, approximately 0.2. That's not set in stone by any means, but it's a guideline to follow. That means that you have successfully chosen a model and you have not overfit the model. Okay, so after we look at the fit summary and we notice that the software has suggested a model, it has an algorithm in here that compares the p-values, the lack of fit, and the R-squareds, and takes into account if the model's aliased, and it will produce a suggested model to you. That suggested model is then carried forward onto the model screen. So you can see that it's going to quadratic. If the two-factor interaction model was the best model, then this would default to two-factor interaction. So the suggested model is a really great place to start. I would highly recommend it. We're going to take this and now we're going to form the ANOVA. So we'll click ANOVA, and here are all our terms. Go back to slideshow. We can see that the overall model is statistically significant. A on its own is not significant, but B and C are significant. There's an interaction that's not significant. Here is an AC interaction that's very significant. Now that's really important. We want to keep terms in the model that are statistically significant, or terms that are needed for model hierarchy. We need to maintain model hierarchy. So we do not need this A squared term, but because AC is significant, we definitely need to keep the main effect A in the model so that it can provide the base for the adjustment that AC is going to do. So we have to know where A is starting from, and then so we have both A and C as the bases, and then that AC interaction term adjusts those effects so it's correct. Okay, so we will get back to model reduction in just a moment. Below the ANOVA, we're doing a check for lack of fit one more time, and we can see that it is not significant. So that is good. Over on the right side of the screen, you're going to get a set of additional fit statistics. One of the statistics is the standard deviation. This standard deviation tells you the amount of variation left in the process after we've accounted for those statistically significant effects. So in this case, the remaining standard deviation is approximately 4. We also get the overall average of all of this percent conversion data, which was 78. And then this CV is the relative standard deviation. And so it is the percentage that the standard deviation is of the mean. So in this case, the standard deviation is about 5% of the mean. Over on the right side, these are the numbers you really want to hone in on, the adjusted and predicted R-squareds. And as I mentioned before, they tell you the amount of variation in the data that's explained by the model or the amount of variation in predictions that's explained by the model. And certainly higher numbers are better. There is no particular lower cutoff. I mean, I won't say that if it's below 0.7, it's bad. That's totally wrong. It's just a probability. We're explaining approximately a certain amount of variation. You want to explain more variation. That would be a better prediction model than one that explains less variation. But if you have a very noisy system, then sometimes your models are simply going to be left with a lot of unexplained variation. That doesn't mean that they're bad models. Sometimes that is absolutely all you can do, and you just have to press forward with those. The lower right-hand corner of that ANOVA screen gives you your prediction equations. And I don't typically go in and look at these prediction equations, but you might need to put them in a paper, a research paper that you're writing, a journal article. I would use, if I was publishing it, I would probably use the equation in terms of coded factors, because the coded coefficients then are useful for interpretation. So I can look at these and see that factor C is the highest impact as far as linear terms, although there is a very large AC interaction. It's almost twice as big as C itself. So very, very big interaction term that's super important. Sometimes people want to whittle it down to just saying, oh, which factor is most important? In this case, you can't do that. There is a combination that's actually even more important than any of the main effects by themselves. So you want to make sure you're looking at all those coefficients. The actual coefficients are nice because they are in the actual units that you experimented in, but they account for differences in the factor ranges, so they're not easy to interpret. You can't easily understand these coefficients. So just don't try to interpret these. If you need something that people would interpret, then you must use the coded equation. Okay. After you have chosen a model, then you want to validate that model using diagnostics. And I won't spend much time on this because I just recently did an entire webinar on all the diagnostics, but we'll take a brief look at these. To begin with, diagnostics are all about something called residual analysis. Well, what in the world is a residual anyway? Well, we take the data that we measure. So in this case, it would be all of the percent conversion values, these responses that we measure. That data has signal in it and noise in it. And we use the ANOVA process to filter out that signal and build that polynomial. That gives us the model. From that model, we can then make predictions. Okay, so we've taken our data, built a model, we're making predictions. We are then going to compare those predictions to the original observations. And the difference between the observed data and the predicted data for that particular run is called the residual. So it is the noise in your system. Now, it is these residuals that should be independent, normally distributed with a mean of 0 and a constant variance. Okay, so that's kind of the statistical mantra. Some people say, might make the mistake of saying, oh, in order to use DOE, you must have, your data has to be normally distributed. That's wrong. That's absolutely wrong. In order to use ANOVA, the residuals need to be approximately normally distributed. Okay, and if they're not, then we can do things like a data transformation. But the raw data itself does not need to be normal. Okay, so we have a set of standard diagnostics that we use. The first one, we take those residuals and we plot them on a normal probability plot. And we want the residuals to be an approximate straight line, which holds true in this case. You know, the ends are just a little off the line, but not bad at all. Pretty straight line here. And as a matter of fact, you can find the statement in textbooks in the DOE diagnostics section that says that ANOVA is robust to moderate deviations from normality. Okay, let me repeat that. ANOVA is robust to moderate deviations from normality. That means that, you know, there can be some wiggle up and down pattern here, a little bit tailing off on the ends, and it's no big deal. We're quite robust to this particular assumption. Now, we're a little bit less robust on the residuals versus predicted graph that is looking for constant variance. So that means that we're plotting our residuals against the predicted values. So down here, we're going from 40 to 100, and you just want a random scatter, no particular pattern. What you do not want is the residuals to be increasing as you go from the low end to the high end. So if they're increasing, that would show kind of a horn or a bell shape, and that indicates that you have non-constant variance. Okay, so that would indicate probably a need for a transformation. Now, normally underneath this residuals versus predicted, there is a residuals versus run. And I pulled that down. If you didn't know, these are draggable. So I just grabbed that particular graph and pulled it down, put it down here in the lower right corner. And again, we're plotting our residuals versus time order, run order, and they should just be, again, a random scatter, no particular pattern. You are watching for big blocks or groups of runs above or below the line. You're looking for slopes, you know, any non-random patterns. So no pattern at all is the perfect shape. In addition, both of these graphs have red lines on them. These are a little test for outliers. And so you want all of your data points to be within the red lines. I don't consider anything to be an outlier unless it's actually outside the lines. So, you know, you say, oh, this is getting close. No, it's not. Don't even consider it to be an outlier unless it's actually outside those red lines. And just by the way, the location of those red lines changes depending mostly on the number of runs. So a larger design is going to have these lines tightened up, and a smaller design, like an 8-run design, is going to have those red lines spread farther apart. Okay. The fourth plot, which is super important to look at, is down in the lower left-hand corner. It's called the Box-Cox plot for transformations. So it evaluates a series of transformations like the inverse and the inverse square root and a square root and a log, just a set of transformations, and tries to identify the transformation that gives you the least amount of error. So this line is a line of error, and wherever it's lowest, that would be the theoretical best transformation to use. In addition, we calculate some confidence interval, 95% confidence interval. Only one red line is on here. The other red line just happens to be a little bit off the graph. And any transformation within those red lines is statistically the same. And so in this case, our recommended transformation is none, which we're currently using. So there's no need to try a different transformation. It's not going to improve the statistical analysis. So those are the 4 graphs that I always look at. Should only take a few seconds to look at them. Now, in the bottom right-hand corner is a set of influence graphs. Okay, so note that diagnostic graphs, the 4 we're looking at here, are used to validate the ANOVA. If there are problems with the graph, with outliers especially, if there are problems with outliers, then a second level of graphs is the influence graphs. So I am going to put those. I've now pulled each of those out. Here's Cook's distance, here's leverage. I've pulled out those 4 graphs into their own little cell. And I'm going to look at leverage first. So each of these influence graphs measures the amount of influence of each point. Now, first a comment about influence. A high influence point is does not mean it's a bad point. If you in your group of friends have high influence on your friends, is that a good thing or a bad thing? Well, it depends. So influence in and of itself is not bad. People tend to overreact to this, to these graphs. They say, oh, if I have a point like way out here, that must mean it's bad. No, it means it's influential. If that data is a really good piece of data, if it's perfectly predicting the process, then that influence is really good to the model. Okay, so you have to be careful in interpreting these. Okay, the first one, this leverage one, shows the influence shows the change in our predictions due to the position of the design. So things like center points, here's actually these 4 down here and these 2 here, those are all center points and they're replicated. So because they're replicated, they actually reduce their individual influence. They have less influence because there's, I think, well, there's 6 of them. So they have less influence because they're replicated. Then all the other factorial points and axial points have pretty much the same amount of influence because they are the same distance away from the center, so they will have equivalent influence on the predictions. Okay, now Cook's distance indicates the change in how the model fits, either with or without the point. So these three that are in yellow, you can see they all say with and without the point. That indicates that they are all deletion statistics. We are testing in this case, the model fit with and without the point. And so some of them are a little bit more influential. Down here, DF fits, we're testing the predictions with and without the point. So this one tests the model fit, this one tests predictions that we're making, and this third one tests the change in each coefficient. So the DF betas is one where you actually have to change which coefficient you're looking at, A, B, C. There's a little pull down here that you can change that. Okay, so that was a few minutes on a set of influence diagnostics that I actually don't expect you to look at. But people look at them inadvertently and get concerned about them, and you really shouldn't unless you're trying to understand the influence of a particular point that's giving you some concern. But generally, I would just ignore that information. Okay. So let's back up a little bit. I want to back up to the ANOVA, and I want to consider removing the non-significant terms from the model. Okay, so I am going to get back to the software, and I'm going to go back to my model screen. And Stati software has some automatic model reduction methods. They are under this auto select. And I would consider this a best practice to use it most of the time. The easiest one to understand is one called p-value backward. And I'm just going to let this thing run and show you what it's doing. So I'm going to click Start. And it looks at all the p-values for each term, and it finds the terms that have the biggest p-value. That means they're least significant. So the AB interaction had the biggest p-value at 0.17, and so it says selecting AB to be excluded. Okay. When it excludes it from the model, it puts it into the residual. So it just moves it down to the residual. And then all the p-values are recalculated. And then it looks again and says, oh, A squared is the next one, the next biggest one. So it takes that one off. Then it looks at all squared terms and two-factor interaction terms as a group. It looks at them first. It says, okay, I'm done with those. Then it looks at main effects, and it finds that A sitting there could be excluded. Okay, so it removes those terms. You click accept, and you can see that it's taken them out. What it does not do is it does not check for hierarchy. So you still need to make that step. You need to correct this. So do you want hierarchy corrected automatically? Yes. That puts A back in the model. But the other two are out. So we no longer have A squared. We no longer have the AB interaction, but we do need A to be in the model to support this AC term right there. Okay, so after that adjustment is done, then you double check your lack of fit, you double check your R squareds, and they should all look good, and you double check diagnostics. Make sure everything looks good on the diagnostics, which it does. Okay, There are a couple of other options when you want to change options. You always need to set your process order back to the original, set it back to quadratic. We could take this p-value method and go forward with it, which means it starts with an empty model and it builds up by adding the most significant terms. So you can see what it does. It says it started with the intercept, and then it found that C was most significant, so it put C in the model. And then it starts looking at the interactions and squared terms, and it adds those. And actually here it found B, it added that. So it's just adding terms one at a time. So we accept that, and again you say yes to hierarchy, and you'll get the same model. If you have run a well-designed central composite design, or box blanket design, or something like that, or a well-designed optimal design where there's minimal correlations between the terms, then all these different criteria and selection methods will give you the same model. They give differing models if you're just trying to analyze some historical data, where there might be some correlations between the terms in there, correlations between the factors. Okay, so those p-value is a very, very common traditional method. There is another method that has become very popular with statisticians these days called AICC. And that's the one I default to now. It's just another statistical criteria. I can't even explain exactly how it's working, but it has proven to be really just as good as p-value, and in some cases better. So I do tend to use it, and it's got the same either backward or forward methods. You either take your full model and reduce it, or you build up your model. I tend to like taking the full model and reducing it, eliminating terms. But that, again, is going to do the same thing and give us the same model. Okay, so if you grab these slides later on, you'll see there's a summary here. There are a couple other methods too that I never use, but they are in there for researchers who want to do some of the comparisons. We recommend going with the default criterion of AICC and use the selection method of backward. If you do have a lot of correlation in your data, then try several methods. Compare methods. Compare the models. If the models agree, then you're in good shape. Otherwise, just do some comparison, and you might have to do confirmation runs to figure out what model will work. Just a reminder that all model reduction should be guided by the subject matter knowledge. Always ask yourself, does it make sense that these terms are in the model or not in the model? Subject matter knowledge is super, super important. Okay, so once we have chosen a model, double check the diagnostics, then we are going to look at the model graphs. And there's a variety of model graphs with a response surface design. I'm going to tend to use the contour plot and the 3D surface plot. So the contour plot, looking at it in these two dimensions, we've got B, factor B, and C on this graph. And the percent conversion is shown as various contour lines. So I can see I've got 67.5, 70, I've got 75, 80, 85. And I am trying to maximize my percent conversion. So this response I want to maximize. So in the BC direction, I would tend to want to go towards the area that's more orange. I circled here, up in that area. And if you make this into a 3D surface, then you can see that. And you see there's kind of a slight bend here. That's that C squared term that's giving a little bit of bend. Okay, so here's the contour, and the picture that I showed in my PowerPoint had a lot more contour lines on it than this one. You can add contours. You can edit your contours, so you can add a lot more as you like. So you can just add them manually, or you can set the contour value to be a specific value. So I right clicked and chose edit, and I'm going to make that be exactly 79. So I've got 79, 80. And I might want this one to be exactly 82. So whatever you like. And then there's the 3D surface. This is a different view. This is the AC view. So, my best area is up in that corner now. All right, so if we want to be up in this area, then the last step that's super important is to do confirmation runs. The final stage of a designed experiment is to confirm that the model predictions are accurate in the original process. Now, depending on what you're interested in, you might choose to confirm a few runs right at an optimum location, or you might spread some confirmation runs across the design space. There's no right answer. It's what you want to get out of this analysis and out of this, going back to why you ran the experiment. If you're looking for a specific point, then you can confirm a few runs right at that point. But oftentimes people want to kind of understand how the process works across the whole design space. And so then they might want to spread confirmation runs out and sample in different areas. So what we're going to do is we're going to go down to post analysis, and we're going to go to the confirmation section, and we're going to verify that the mean or average of several confirmation runs falls within a 95% prediction interval. Okay, so this is what I'm going to do. I'm going to enter the process conditions that I want, and I'm going to enter some run data, and then we'll look at the results. So on the left side tree here, I'm going to go to confirmation, and I have chosen a spot that I want to evaluate. So I typed these in: 50, 90 temperature, catalyst of 3, and then I decided to do 4 runs So I had to go out to the process and physically run the process and estimate my percent conversion 4 independent times. And I got the data for that, put them in, and then down at the bottom, it calculates the data average, 92.6, that's the average of those 4. And then the window, the 95% prediction interval, ranges from 87.7 to 105.9, and our average is within that window. So we can say that we confirmed this analysis, that the analysis is making predictions well, and you know, we have good results. Okay, so that final confirmation is really important to do. If that data mean is outside of the interval, this will actually turn red. An obvious question is, what if confirmation fails? You know, what if I get that red number? Then you really kind of have to go back and, first of all, double check your analysis. You know, did you have some significant lack of fit? How high was that predicted R-squared? Did the diagnostics look good? Were there any outliers? Did you need a transformation? All of those things. Double check the analysis. Okay. Then, next thing to think of is the process. Did the process stay the same from the time you ran the experiment to when you're doing the confirmation runs? Or did it shift? So do you have a stable process, or does it float a bit? Another thing to consider, are there other process factors that you did not include in the experiment that might be affecting the system? They might be causing variation, they might be causing shifts, they might, you know, be causing, you know, just the system to be different than what you expected it to be. So if confirmation fails, then you really need to take an engineering or scientific look at the system and decide how you can get better data. You know, often people spend a whole lot of time on the analysis standpoint and trying to figure out, how can I get this analysis to be better? Well, often you can't get the analysis to be any better. It just is giving you the correct analysis for the data that you gave it. And if your data isn't good or reflective of the system, then, you know, the analysis is just going to be as good as the data that you give it. Okay, so before I do a little wrap up, let me double check the questions here. We'll see what's come in. So give me a second to read some of these. So question that came in early, is there a benefit of running an RSM if you've already completed a resolution 5 or higher design with center points and did not find curvature? Probably not. The whole point of adding center points to a factorial design is to have that decision point about, do you have nonlinearity? If you have nonlinearity, if you detect curvature, then you run the response surface design. If you don't, then I would probably go with just the best conditions out of the factorial design and decide if you want to move and do a different type of design, you know, recentered on the best location, or if you're happy with the results. But going forward there, that's really a business decision of how you want to proceed forward. But that's, the center points are intended to be that kind of pass, fail, or go, no go thing. excuse me while I'm reading a few questions. Some of them are a little bit longer. Okay, so somebody wrote in, they have a response surface design with a significant p-value for the quadratic model. They have high adjusted and predicted R-squareds, but lack of fit is significant. What does this mean? Well, the first thing I would look at are your replicates. Are your replicates, where they run independently? Are the replicates representing the pure error of the system? So I would look at that and make sure that the replicates were run correctly and as expected. There's nothing from a statistical standpoint you can do to fix a significant lack of fit. You're just going to have to decide if the predictions in the area that you want are good predictions or not predictions. Somebody else said, I see that there's some cubic terms that do not seem to be aliased. I'm just going to make a comment that all the cubic terms really are aliased, even if there's not check marks by them. I'm going to show you where to see that a little bit better. So we're going to go to evaluation of this design, and we'll go to a cubic model. And so we put in all of those cubic terms. There's a lot of them. And we'll click on results. And we'll click on aliases. And the only cubic term that could be added would be the ABC. All the other cubic terms are actually aliased with each other. So adding in one particular cubic term is not appropriate, because it really is aliased with these others, and you can't separate it out from any of the rest of them. So any design like a central composite or a box Benken design, they are limited to just quadratic model. There's a question about choosing a random effect for the block. Since there's only 2 blocks, trying to analyze that block effect as a random effect, there's just not enough information there to estimate that random variable. So no, I would not choose to estimate the blocks as random when there's just 2. If there were a lot of them, then that might make sense, but it takes away a lot of degrees of freedom from the system that can be otherwise put to use for other things. A question says, if we don't have any idea about the existence of interactions, can we use a Plackett-Berman design? Absolutely not. That the only time I would consider using a Plackett-Berman design is if you absolutely know that you do not and cannot possibly have interactions, because otherwise with the Plackett-Berman design, your interactions are confused with your main effects. So it'd be a very poor choice. When you are running confirmation runs, they are separate from the design. Somebody asked if you put them in another block, and I generally say no, you don't put them into another block. You want to keep them independent from the rest of the system. to have an independent test. You don't put them in a block. If you put them in the block, then they're included in the analysis, and that would not be appropriate. Okay. If I haven't gotten to your question, I will try to answer it via email through our stat help. And otherwise, I appreciate the time that you spent with me here today. We want to make sure that all statistical analysis is guided by subject matter knowledge. Does it make sense that given terms are significant? Do the model graphs reflect the actual process? Do the confirmation runs verify the analysis? Those are all the things that you need to consider when you're doing your analysis. If you want some more resources, I recommend the RSM Simplified textbook. You can get that from the publisher or else from Amazon. And it's available in hardcover, softcover, and as an ebook. Self-study options to learn more. Check our YouTube channel if you haven't already been on there. Statistics Made Easy by StatEase. Check that out. The top playlist is new to DOE, and it's a great collection of webinars to look at on a big variety of topics. The other thing is we have our StatEase Academy. You can go to our website under Training and Academy. These are self-paced online courses. Just covers the basics of factorial and fractional factorial designs, but those are available free of charge. So you are welcome to jump into those and kind of improve your DOE know-how. If you have any additional questions, please send them to stathelp@statease.com and one of us will be able to answer them. So thank you very much, and I hope you enjoy the rest of your day.